with that, our next speaker is Uçak from the Fraunhofer Heinrich Hertz Institute. So yesterday we heard from Fraunhofer in Bavaria, now we are in Berlin. Utku is working on uplink multi-user MIMO, and he will now talk about that. Thank you. Maybe a round of applause.
Thank you, Robert. Yes, today, good to be here and to give the talk. I will talk about our internal development of the uplink multi-user MIMO using SRS channel estimates in OpenAirInterface. And yeah, let's begin. So we built a real-time 5G NR compliant uplink multi-user MIMO testbed, which is these things are usual in this crowd, the real-time and the NR stuff using SDRs. But we did this because there was no multi-user MIMO open source testbed, which is also changing now with you seen the demo yesterday. But we have some other long-term motivations than the current Eurocom development. So we used the SRS channel estimates for the uplink combiner computation, because we would like to scale the system up for a self-free distributed MIMO system. And we want to use the TDD reciprocity and decouple the uplink and downlink a bit, like it is for the data in the uplink. And so we would like to validate SRS as a beamforming SDMA scheme for MIMO before going on to the downlink, reciprocity-based downlink. And here's one of our system block diagram, because we had a USRP-based and an ORU-based setup. And in this one is the USRP-based, where you have a 2x2 overall multi-user MIMO, where you have a two antenna G0B and two single antenna UEs. They are both realized with the USRPs. And the G0B side is running in a more powerful PC, also with core network and with the multi-user MIMO modifications. And the other side, we have a smaller PC running two Dockerized instances of OAI UE connected to USRPs. And we have some frequency stabilization peripherals for, namely, like the 10 megahertz reference clock for the G0B side and GPS signal for the UEs. And this is a very similar second system diagram, where we replaced the USRP-based system with a light-on ORU running OAI in the 7.2 split mode, and using commercial off-the-shelf UEs, namely Quectel modems connected to Raspberry Pis. But the overall idea is very similar. And some simple theoretical principles of the multi-user MIMO. The only equations in the slide, where we have this simple subcarrier-based system model, where you have a channel vector transmitted from the UE, the transmit vector transmitted from the UEs goes through the MIMO channel, and then we would like to do linear MIMO detection by doing the linear operation. And we considered two simple textbook cases of combiners, namely the maximum ratio combining or match filtering or the regularized zero forcing, as you can see. The idea is that the H is coming from the SRS channel estimates from the uplink, where you can see a visualization. And the OAI receive loop computes the SRS channel estimates and then use this to compute the combiner matrix. And at the push processing routines, it will apply this as a pre-processing step, so that the interference from the other UE can be cancelled out. There's some IQ constellations, but I will give more details. So this is just some initial idea of the idea. And we have the scheduling modes. The vector graphics did not go well with the PDF conversion, or So, but the idea, I think, is visible, where you have two modes of the scheduling, where you have the classical OFDMA mode and the STMA mode. And the OFDMA mode is the vanilla scheduler of the OAI, where the resources of the two users are scheduled orthogonally. And yeah, we would like to change this so that the two users can get the same resource blocks if they need to get some capacity out of it. And yeah, with our implementation, you can switch between these two modes while the system is running to just verify the effects of the capacity gains, which I will show later. And yeah, some more details on the USRP-based hardware setup is that yeah, we use the N320 as the G-Node B and two B210s with GPS DO plugin for the frequency stabilization. And as processors, we had a NUC Extreme for running the G-Node B and another NUC for the UE controller. And we had the 10 megahertz signal source and the GPS antennas for the synchronization. And yeah, currently we run this with 10 megahertz bandwidth, so 15.36 mega sampling rate with usual 30 kilohertz in 3.3 gigahertz. We support up to 16 QAM at the point, but yeah, the work is ongoing to support higher rates. And the ORAN-based setup is that we use a Lighton RU with two Quectel UEs. The rest is similar, except the PTP switch to connect the ORU to the computer. And yeah, the initial results that we can show is the throughput gain that you observe when you switch between the scheduling modes. So switching between STMA and OFDMA modes gives you throughput gains because now we don't need to share the resources between two UEs. And this can be clearly observed when the system is running because you can switch between the scheduler modes. And so if you look into some phi signals, you can also see this in the different steps of the physical layer processing, where depending on your scheduling mode, you can observe the interference from the other user. As you can see, well, on the left one. And if you just do maximum ratio combining, then it's not enough for the canceling interference, which is, then you also need to do the channel inversion as expected. So this is a validation, nothing surprising here. But if you don't have the interference from the other users, you can just use a MRC combiner to recover your constellation. And yeah, so we get some questions about, like, is SRS enough to track the channel? Like, what about the synchronization artifacts and so on? So we have some, yeah, I can talk about some practical insights about this. Is that, yeah, if your channel is stable enough that you can track with SRS in the order of a couple of slots or like the TDT pattern, then you can use the MRS for fine equalization of the channel after it's after the interference is cancelled. So because of this, we had a two-step equalization. One is from the SRS channel estimates, where you can cancel out the other UE, and then at the MRS-based equalization, which is already inside the push scheduling, the push processing of the OAI. So this gives you the final QAM constellation, basically. And yeah, with this architecture, you can implement this processing as a pre-processing step to the regular OAI processing, which was also a decision to make the implementation a bit more like standalone than changing too much into the OAI processing. And yeah, we had some, I mean, this project took some time. Over time, OAI also gets more stable in the beginning. We had problems with frequency stability when we were using the commercial UEs because you cannot synchronize them with an external reference. And we observed that with the USRPs, with their 10 megahertz or GPS synchronization capability, the result was more stable. But in the recent months with the ORAN-based setup, we also observed that you can also use commercial UEs with this way. So yeah, this frequency synchronization was a big thing, but it gets improved. And also, yeah, this is also some insights that we implemented this currently in the floating point arithmetic, just for the sake of simplicity. And with our parameters, this was good enough to get real-time performance. Probably as a next step, you would keep the combiner computation in float, but use the application to integer arithmetic. So because it happens way more often compared to the inverting the channel, and yeah, it's also more stable because you don't invert a matrix using integer arithmetic that way. And here is like a summary of our the routine, where in the OAI push scheduling or the receive chain usually does this the control channel decoding and then share channel decoding and then SRS, and we modify this workflow, like the signal flow, so that yeah, you still do the control channel first, and then you do the SRS and then compute your combiners from it, and then you can apply this to this combiner to the push signal, and then after this the push processing is carried on as a single antenna case of the regular OAI routine. So this was the very high level architecture. And yes, to conclude, we had this initial multi-user MIMO implementation to extend into a cell-free system. And currently we are working on user grouping and using combing schemes for SRS to get more robust with combining with computing the combiner, and more interesting combiner algorithms than just maximum ratio combining or regularized zero forcing. And of course, increasing the MIMO dimensions, both in the diversity or in the layer case. So, and also we had a AOCNC paper published about this work, so it was also presented 2 weeks ago. If you want to get more details, you can check the paper out, or yeah, we can have a discussion afterwards. So thank you for listening. And, yeah.
Or maybe just speak loud, Rakesh.
Yeah. So.
Well, it's coming.
Hi. So I'm just curious about your results. You mentioned you were using ORAN setup with RU and commercial US. I was just curious about the results, your results in that case. And also, I'm on the algorithmic part, you were using floating point, right?
Yes.
So I'm open to floating point. I'm just curious to know what is the factor of timing difference you get between fixed and floating.
I did not measure this. So for me, the criteria was that am I going to get like USRP real-time issues if I run it like this? And with the bandwidth that we tested this was not the case. So this was good enough for me. And for the results of the ORU or the commercial equipment case, yeah, this was a recent test than the USRP-based setup, where we had more experience, and yeah, it was still, I would say, less stable than the USRP-based thing because of the frequency synchronization thing, I guess. But also in the last time we did this ORU-based test, was the SRS. Yeah. So the last time we did this test was the SRS scheduling was still in a way that the SRS of two UEs are scheduled to different slots. So you get a channel snapshot from actually time, like different times. But since then, we now implement a COM-based SRS scheduling where the users get the channel from the same OFDM symbol. And this also improved the stability in the USRP-based system. So I expect it also improved it in the ORAN-based system. But we did not test this yet.
Okay.
Does this answer your question? Or?
Yeah. Yes. I mean, so you only test till 16 QAM, right?
So far, yes. We limit the MCS so that it will. But yeah, we will once we are like stable enough, then we will increase this as well. But yeah, so far it's only 16 QAM.
Thank you.
Yeah, thank you.